space. No human endeavor has transformed society and defined our place in the cosmos more than the physical sciences. What started as a kernel of knowledge about the movement of the heavenly bodies has expanded to include the atomic building blocks of all chemistry. Geology's understanding of Earth's long history and the forces that have shaped our planet's features. Astronomy's picture of an ever-expanding universe populated by billions of galaxies, each containing billions of stars. And physics' understanding of the basic principles of movement, energy, and forces which have given us the technological world of cars, planes, television, computers, cell phones, and the electrification of the planet. Turning Points in the Physical Sciences takes you on an exciting journey of discovery from ancient through classical science to the world of modern physics, relativity, chaos theory, and quantum mechanics. The world of classical science is one of simple systems. For example, two magnets sit on a lab table next to each other. Push one, and the other moves in a predictable way. But what if there were 5 or 20 magnets? How would they behave? Would their movements be predictable? It was a matter of faith in the scientific world of the 19th century, but if one of the magnets was moved, the movement of all the others was, in principle, predictable. But was it really? In 1903, French mathematician Henri Poincaré set about studying the famous three-body problem, predicting the movement of a simplified solar system consisting of a sun, moon, and earth governed by Newtonian laws of motion. What Poincaré found was that even this simple system behaved in unpredictable ways, and that the three-body problem was unsolvable. Understanding this and other more complex systems, such as Earth's weather, would have to go in another direction. That direction was a new brand of science called chaos theory. A theory whose main premise was that small changes in initial conditions could result in vast differences in the final outcome. Chaos theory remained a curiosity until the advent of high-speed computers and computer modeling in the 1960s. In 1961, Edward Lorenz was modeling the Earth's weather with a computer and found that the smallest change at the 1/1,000,000th of a decimal point could make his predictions useless. He called this result the butterfly effect. In the Amazon, a butterfly flaps its wings, and 2 years later, a thunderstorm appears over Kansas. No flap, no storm. The butterfly effect is everywhere around us. Consider a pile of garbage. Try to imagine all the events that must have occurred to result in just this pile of material. Suppose, for example, that Ray Kroc had never been born and consequently gone on to found McDonald's. In the 1970s, Benoit Mandelbrot added fractals to chaos theory. Fractals are the byproducts, the patterns left behind by dynamically changing systems. Fractals are self-similar as illustrated by these designs. Their inherent property, as with clouds or coastlines, is that no matter how close or far away one gets, the basic pattern is always the same. At the end of the 20th century, the pendulum had come full circle. The long road to the discovery of the simplicity behind the complexity of everyday life had been reversed. Using a computer, one could start with a simple system, such as colored squares on the board that change by simple and known rules. In time, life-like complexes emerge. Self-organizing clusters come into play and interact with each other. Structures are formed that are always on the edge of sudden and radical change. This is, in fact, the way ecosystems, human societies, and even the stock market behaves. Chaotic systems are deterministic, but inherently unpredictable. At the beginning of the 21st century, chaos theory is ripe with philosophical suggestions. But whether it alone or in combination with quantum mechanics will yield new technological advances remains to be seen. The most promising area is perhaps in artificial intelligence. However, chaos theory has the advantage over the other two major branches of the new physics, quantum theory and relativity, in that it seems intuitively correct, reflecting the unpredictability of human behavior. It's been said that he was a rather undistinguished student and a minor bureaucrat at the Swiss Patent Office. But in 1905, he put forth the most revolutionary theory in all of science. It was called special relativity. Albert Einstein had no laboratory, no instruments. His experiments were done in his head. They were thought experiments. What Einstein did was put together two experiences, one common and the other bizarre. The common experience is based on the observation that when we travel in a jet, we don't notice in the cabin that we are traveling over 350 miles per hour. Everybody operates in the cabin as if they were at rest on the Earth. In scientific terms, Einstein stated, "The laws of physics hold in all non-inertial frames of reference." As for the more bizarre observation, Maxwell's equations held that all electromagnetic radiation, such as radio waves and X-rays, travel at a constant speed, no matter how fast the source was moving. Now, that doesn't seem right. If a person were standing on a moving train and threw a baseball, the speed of the ball would be the sum of the train's speed and the speed of the pitched ball. But if the person had a laser gun, no matter how fast the train was going, the speed of light emanating from the laser gun would always be the same, 186,000 miles per second. In special relativity, nothing can travel faster than the speed of light. It is a constant. Einstein reasoned that if the speed of light was fixed, then something else must be variable. And it turned out to be space and time. 4 correlates derived from special relativity have changed how we look at the world. Einstein saw that first, space was not absolute, and second, neither was time. The relativity of space and time is illustrated by the well-known twins paradox. Twin brothers on Earth are about to part ways as one is going to make a super-fast trip on board a spaceship to the nearest star and back. From the standpoint of the earthbound twin, he sees his brother not only begin to shrink, but also slow down as he speeds away. Oddly, looking back from a spaceship, the traveling twin sees the same thing happening to his earthbound brother. In short, dimensional measurements, whether of space or time, are relative to the frame of reference of the measurer. Interestingly, in the twins paradox, when the brothers are reunited, the earthbound twin is older than his traveling counterpart. However, the most mind-boggling aspect of special relativity is that the common sense notion that simultaneity of events between people can be shared, as when a bus passes in front of people, is wrong. In short, at any given moment, there is no one fixed set of events. Everything is always relative to each observer. Finally, special relativity gave the world E equals mc squared. Tiny bits of matter can release huge amounts of energy, as was demonstrated by the atomic and hydrogen bombs. 10 years later, Einstein stunned the scientific world once again with his theory of gravity. General relativity answers the question, how does the moon know that the Earth is out there? The problem was that gravitational attraction between two objects seemed to be acting instantaneously. Such an action was not allowed by special relativity, since no effect could travel faster than the speed of light. To solve this contradiction, Einstein proposed that objects bend space and time. The reason a small object is drawn to a more massive object is that it's like rolling downhill into the dent made by the big object in space. Throughout the 20th century, special and general relativity have been proven over and over as the correct description of how the large-scale universe works. Ten years after the discovery of radioactivity by Pierre and Marie Curie, a new branch of physics, nuclear physics, was developing rapidly. Radioactivity, detectable by a Geiger counter, was the spontaneous disintegration or decay of the nucleus of certain elements such as uranium or thorium. In 1907, American chemist Bertrand Boltwood discovered an important property of this radioactive decay. It occurred at a constant rate. In a predictable time, a radioactive element such as uranium would end up as lead. To understand this, suppose we have 50 pennies representing uranium. Toss them all onto a table and remove the ones that turn up heads. Heads represent a conversion to lead. Repeat the process. As we can see, this results in a random but predictable over time halving process. In radioactive decay, each radioactive element has a unique halving process called its half-life. This chart shows the decay of uranium-238 into its final stable form of lead. As one can see, half-lives of different elements vary from millions of years to minutes. In fact, some of the man-made radioactive elements produced in giant particle accelerators have half-lives of less than a second. Boltwood postulated that the ratio of lead to uranium in a rock sample could be used to calculate how long ago the rock was formed. Geologists now had an accurate way to date the Earth. In 2001, a 4.4 million year old rock was found in Australia, making the Earth at least that old. 40 years after Boltwood's discovery, American chemist Willard Libby developed a radioactive tool for dating anthropological events. By 1940, it was known that cosmic rays produced, in small amounts, a radioactive form of atmospheric nitrogen that ended up as a carbon dioxide isotope called carbon-14. Cosmic rays are made up of high-speed electrons, protons, and helium nuclei, also known as alpha rays. Some cosmic rays come from our sun, but most are a byproduct of the creation of the universe. So as a result of cosmic rays bombarding the Earth, radioactive carbon-14 is constantly being incorporated into living things. But once death occurred, incorporation ended, and with a half-life of 5,700 years, carbon-14 decays into stable carbon-12. By measuring the ratio of carbon-14 to carbon-12, scientists now had an accurate way of dating organic material that was less than 40,000 years old. Anthropologists could now say with confidence that Tutankhamun, a pharaoh of the 18th dynasty, lived from 1361 to 1352 BC and was buried in the Valley of the Kings. Or that the Shroud of Turin was a medieval forgery. At the start of the 20th century, a number of Earth geophysical phenomena, such as earthquakes, like the 1906 tremor that devastated San Francisco, puzzled geologists and geographers. Surprisingly, these phenomena would be brought together under one umbrella theory 60 years later. Since the early 18th century, map makers had noticed the similarities between Africa's west coast and South America's east coast. It was easy to imagine South America's bulge fitting into West Africa's indentation like pieces of a jigsaw puzzle. But was it merely a coincidence? Also, paleontologists had recognized an odd distribution of fossils across many of the continents. These 250-million-year-old trilobites were found both in the middle of North America and in northern Africa. How were these and other similar fossil distributions possible? And it was known that earthquakes and volcanoes occurred in specific regions on the planet, often associated with mountain building. Were all these phenomena related? In 1912, the German geologist Alfred Wegener proposed that all the continents were once joined into one giant continent called Pangaea. Then, over vast geological time, they had drifted into the present-day positions. This idea of continental drift received little early support, but as the analysis of the Earth's interior developed, it became clear it was not a uniform ball of matter. Instead, it was made up of three distinct layers: a thin outer crust, a denser semi-solid rock mantle, and a hot inner core of nickel and iron. A core that rotated and produced the Earth's magnetic field. The outer layer, the crust, was discovered in the 1960s to be cut into large movable plates. In 1967, Dan McKenzie synthesized this movement into a theory he called plate tectonics. Plate tectonics demonstrated that earthquakes, volcanoes, and mountain building were the result of various crustal plates colliding with each other. In fact, the San Francisco earthquake was the result of the North American and Pacific Ocean plates sliding against each other. And indeed, Africa and South America were once joined, and the reason those trilobites are the same is that North America and Northern Africa were once close together. Today, the movements of the continents over geological time have been tracked by geologists. By the end of the 20th century, a new theory suggested that the Earth's core was like a nuclear reactor, perhaps powering the movements of the continental and oceanic plates. Unlike Einstein's theory of relativity, which redefined space and time, quantum mechanics did not arise from the genius of a single mind. Instead, it emerged from a cadre of founding fathers over a period of years from 1913 to 1930. Men such as Niels Bohr, Werner Heisenberg, Louis Victor de Broglie, Erwin Schrödinger, and Paul Dirac created a powerful but strange theory of the microworld. At its core was the atom. The atom is the basis of all matter. It is what all things in our world are made up of. But what is an atom? In 1913, Danish physicist Niels Bohr presented a new model of the atom, one that had electrons orbiting the nucleus in fixed patterns or orbits. Electrons were restricted to just those orbits and nowhere else. These orbits contained more electrons as they moved from the center outward. In this model, electrons can only move from one orbit to another. When an electron moves from a lower to a higher orbit, it absorbs energy at a fixed frequency. Moving from a higher to lower orbit, a small amount of energy is lost. This energy is converted to light, also of a fixed frequency. Bohr called this movement of electrons between orbits a quantum jump, since electrons are never found anywhere but in one of their orbits. The random jumping of these electrons produced for each element the exact spectral fingerprint of absorption and emission lines discovered by Fraunhofer in the 19th century. Bohr also required that there was a lowest possible stable orbit with a single electron. It was soon clear that quantum mechanics could produce powerful results of the happenings in the macro world, such as explaining and predicting all chemical and heat interactions. Still, it was reasonable to ask, what is an electron or proton? Objects in the real or macro world, such as a moving car down a road, are found to have an exact location and momentum at any given moment. However, when it comes to subatomic particles, the story is quite different. In 1911, British physicist Charles Wilson invented the cloud chamber that allowed physicists to see the fuzzy paths of electrons and other small particles. But when it came to pinning down an electron at any given moment, scientists found that it was impossible to measure both the precise location and momentum, mass times velocity, for an electron. Interestingly, to know both is exactly what it means to be real, that is, to be an independently existing object. What the German physicist Werner Heisenberg found was that determining precisely one value made it impossible to determine precisely the other value. This was Heisenberg's famous uncertainty principle, and it applied to every object in the atomic and subatomic world. And, as if this wasn't enough, quantum physicists now had two ways of describing light, one as a wave and the other as a particle. This appeared to be a fatal flaw in the formulation of quantum mechanics, especially when the Austrian physicist Erwin Schrödinger and other quantum physicists showed that all particles of matter, such as an electron, were also waves. Niels Bohr and others resolved the issue by putting the observer, or experimenter, and their experimental apparatus into the picture. The two fundamentally different descriptions were just the result of the way we looked or performed measurements in the micro world. English physicist Thomas Young's way of looking produced interference patterns in light waves, whereas the bubble chamber produced the trail of a particle. Bohr said that these two ways of looking are not contradictory, but complementary. By 1930, English mathematician Paul Dirac and others had unified these two complementary aspects of reality into one set of equations. As a wave, an electron was, in effect, everywhere, pure potential. But when an experimenter measured the electron, it would appear randomly in one of its possible locations. Needless to say, quantum mechanics challenged our view of reality as no other physical theory had before.